Hello and welcome to the Biuret Assay experiment. First, for the Biuret assay, we are going to use that reagent to detect the presence of peptides in our solution. So we are going to assess the protein concentration of our solution. We are going to utilize Biuret, which is two coupled urea molecules, as shown right here, as well as a copper tartrate complex. So copper is going to form a complex with these tartrate anions, and we're going to make sure we have basic conditions so that our tartrate remains deprotonated, and we can actually couple our Biuret to the copper, and the copper can actually couple with the peptides. So looking at the Biuret complex in more detail, once we have our reagents and we have a peptide chain, that copper, which has been stabilized by our tartrate, can now essentially transfer its bonds and connectivity from the tartrate to the Biuret complex as well as the peptide. And notice that we have more than one amino acid in this sequence. So some will say 2, some will say 3, but we usually need at least a 3 peptide chain for the Biuret complex to detect the concentration of protein in solution. All right, let's go ahead and jump over to the experiment.
All right, this is the Genesis 20. So this is essentially measuring the absorbance of our solutions. So the first thing we're going to do for this experiment is actually set this to a 550 nanometer absorbance. So I'm just going to increase this number until we get to 550 nanometers. And that is what we're testing as we run it. So once we're set, obviously the absorbance there is beeping. We need to basically re-zero it. So we need to let the machine know what zero absorbance should be. I've added water to this. So we're essentially deleting any interference from water and the plastic of this cuvette to test it. So I'm going to set the absorbance to 0 now. It's setting a blank. And so now water and the cuvette are essentially not going to be part of the absorbance calculation this instrument receives. So once we take this out, we can then use this cuvette for other samples, but first we have to make the samples. So next we'll talk about setting up the experiment.
For making our protein solutions, first we want to make a table of different protein concentrations so that we can compare our unknown samples to that and match it up to predict what the unknown protein concentrations are. So to make our table, first we need to figure out what amounts of our concentrated BSA to use and how much water to dilute those with to make our range in concentration from 0 to 10 milligrams per milliliter. So if we want a concentration of 0 milligrams per milliliter, we just want to add water. We don't want any of our BSA in solution. So our BSA is the protein complex that is going to be coupling with the copper and Biuret reagent to actually show an absorbance. And for our 0 standard, with 0 concentration, we don't want any of that coupling with it. So that one was pretty easy. The other one is the 10 milligrams per milliliter. Since our BSA already came with that concentration, clearly we need all of that, so 1,000 microliters or 1 milliliter, and we don't want to dilute that with any water, and that'll give us our concentration of 10 milligrams per milliliter. All right, for the next one, let's look up a calculation to show how to do that using the C1V1 equals C2V2 calculation. So if we want, looking at our range here, we've got 0 here, 10 here, so 2, 4, 6, 8, that'd be pretty clean. If we could make our concentration within that range, that'll cover all the numbers we want to look at. So I'm actually going to go ahead and fill that out, 2, 4, 6, and 8. So that gives us a range from 0 to 10 milligrams per milliliter. So let's do the calculation for the amount of protein solution and the amount of water we need for a concentration of 8 milligrams per milliliter. All right, so using C1V1 equals C2V2, we can calculate the volumes necessary to make the two concentrations that we know that we want. So C1V1, I'm going to make that our concentrated BSA solution. So C1 is 10 milligrams per milliliter. Put that in parentheses there. So 10 milligrams per milliliter. And then the question is, what volume of that do we need to make what we're looking for? So I'll call that V1. And then that is going to equal C2V2. So for C2, we know the concentration we want, and that is 8 milligrams per milliliter. So 8 milligrams per milliliter. And then also, we know the total volume of that we need. So we need 1,000 microliters of total volume for that 8 milligram per milliliter concentration. So now the question is, when we solve this, what volume of our concentrated BSA do we need? So if we solve the other side here, this will give us 8,000. So basically 10 V1 equals 8,000. And so if we divide both sides by 10, 8,000 over 10 is going to equal V1. And so 8,000 divided by 10 is 800. So in that case, then V1 equals 800. And I left this here in units of microliters. Our milliliter units canceled, so we end up with microliters. So again, that is going to be 800 microliters of our concentrated solution to make our 8 milligram per milliliter solution. So the amount of protein solution we need to add is 800 microliters. We know we need a total of 1 milliliter or 1,000 microliters. So 1,000 minus the 800 of this we have leaves us with 200 microliters of water that we need to add.
In the first test tube, we want 1,000 microliters of water. So here we have the P1000. And I've got this set to 1, which is 1,000 microliters of water, 1 milliliter of water. So I'm going to add this into the first test tube, and then I'm going to keep scaling down from here. So next we need 800 microliters of water. And then 600. And 200. And 0 in the last one. So now that we've got enough water in all these, we need to take our BSA standard, and we're going to add our standard to the rest of these. So from our BSA standard, it's set to 200 microliters. That's going to go in with the 800 microliters of water. So we've got 200 microliters there. Going to add that in and flush it through to make sure all that's released. And now 400 microliters. Goes in this one. And 600. So here. I've got 800 microliters. And And now I need the full concentration in the last one, so I need to go back up to 1,000 microliters for the last test tube.
All right, for testing our unknowns, notice that for our original table that we're looking at, we have between 0 and 10 milligrams per milliliter, but we know that our unknowns are much more concentrated than that. They're essentially off of the scale of the standards that we're testing. So we need to dilute those down so they're at least within the scale and we can have a decent estimate of what those actual concentrations are. So fortunately, we were given the approximate concentration, so we don't have to run it and then see what it looks like and then adjust from there. We can go ahead and make an adjustment, shoot for about 5 to 6 milligrams per milliliter, and then go ahead and run the test. So for unknown 1, if we have 12 milligrams per milliliter, that's the concentration. We'll call that C1. So 12 milligrams per milliliter. The question is, what volume of that do we use? If we want the concentration, and just to make this simple, I'm going to go with 6 milligrams per milliliter. Ideally, you'd shoot for 5, but this will make it an easier dilution, and we want 1 milliliter of that volume 2. So I'm going to go ahead and just specify that this is in units of milliliters, and this C1 is in units of milligrams per milliliter. And then C2 is also going to be in units of milligrams per milliliter. All right, so we've got C1 V1 equals C2 V2. So we're going to solve for X. So we've got 6. 6 times 1 is 6. So we are going to then divide that by 12. So basically we would then have 12x equals 6. So 6 divided by 12 is 0.5. So our V1 is V1 equals 0.5, and we had units of milliliters here, so that's what our V1 is. So 0.5 milliliters, and 0.5 milliliters equals 500 microliters. So for our unknown 1, we're going to take 500 microliters of that, and we want a total volume of 1 milliliter or 1,000 microliters, so we'll take 0.5 milliliters or 500 microliters of V1, and then we'll dilute that with another 500 microliters to make our approximate, and this is just a guess, but our approximately 6 milligrams per milliliter solution. We'll then test it and see what that number actually is.
All right, now for unknown 1, I'm going to take 500 microliters. Which means I also need to put 500 microliters of water in there. And for unknown 2, I'm going to take 250 microliters, which means I need to add 750 microliters of water. Alright, now 500 microliters of water for unknown 1. And 750 microliters for unknown 2. So both have 1 milliliter in solution. Now all of these are 1 milliliter solutions. Alright, next I'm going to add 4 milliliters of the Biuret solution to each of these test tubes. I'm going to add it in 1 milliliter intervals, or sorry, in 1 minute intervals though. So I'm actually just going to show the first couple and then we'll stop there, because I'm going to space it so that way when I test the absorbance, time is not a variable within the test. So we want time to be the same for each of these tests. So I'm basically going to take this up to the 1 mark, so I can get exactly 4 milliliters in each test tube, and I'm just going to roll this back the other way to get there. So this is timed, so in another minute I'm going to add to the next test tube. Okay, it's been 60 seconds, so I'm going to go ahead and add to the next. And I'm going to continue this for all of them, including the 2 unknowns. Alright, so you can actually see the color range pretty well for each of these. Essentially, the more concentrated, the darker purple you get. And then it looks like this is falling somewhere in the middle. And after about 45 more seconds, I'm going to add to the final test tube, and then we'll let these sit for 30 minutes. If you get a close up here, you can actually see a more distinct color range where we've got light blue and then it keeps getting darker and darker. Then we've got our 2 unknowns, which actually do appear to be about in the middle, maybe on the upper end here. But we'll test the we'll make our reference graph and then test the absorbance and then corresponding concentration of our 2 unknowns. So starting out, we are going to pull 1 milliliter from each of these solutions. So it'll be, looks like about 2.5 milliliters per sample. Alright, and now this machine is auto-reading the absorbance. So there's actually no button to push there, but we do need to record it. So for our 0 absorbance, we have 0.036. And then each time we will rinse this out into our waste beaker that I have in the sink. Alright, now after 1 minute, we're going to get the absorbance of the next one. And we're at 0.194.
All right, for the experiment we just completed, we have our concentration of 0 to 10 milligrams per milliliter of our BSA, and we have absorbance values for each of those concentrations to give us our standard curve, and then we can look at our unknowns and fit those to the curve to figure out what our unknown protein concentration is. We ran this again in lab. Ideally, if you're looking at this before lab, you'd want to restart your second set about 5 to 10 minutes into the first, so that way you can sequentially just measure your second set of absorbances. In this lab, I just did another one after we were done filming the first, so it took a little bit longer, but it wasn't quite as overwhelming to think about with all the recording. Anyway, now that we have our absorbance values, we can graph these. So for graphing them, we want to select the data that we want to graph, essentially to make our curve, so we can then use the y equals mx plus b equation to figure out what concentration these absorbances equal. So in Excel, you're going to go to Insert, Graph, a scatter plot is good, and that gives you a scatter plot. Now, unfortunately, this also gives two separate lines. So Series 1 and Series 2, you've got two different data sets. It looks like Series 1 is blue, considering that blue has a lower absorbance than that, which means if we were to go ahead and directly add our trend line, or y equals mx plus b equation to this, we would only be fitting it to this one series. So let's go in and select data again, and we are going to add a data set to this. So we're going to call this the combination, and for our x values we want our concentration, and we actually need to select this twice because this is going to correspond with two sets of y values. So I'm going to add a comma there and select it one more time. And then for our y values, we are going to select absorbance 1 as the first, and add a comma, and select absorbance 2 as the second set. Alright, so now our combination set has both of those values. It's actually overlapping with Series 1 and Series 2, so we don't need those on there anymore. Let's go with that, and now we hopefully only have our combination data set displayed, which it looks like we do. So if you look very closely here, you can see there's actually two dots at the concentration 10. Here, this first absorbance was 0.561, the second was 0.551, so that makes sense there would be two spots there. So all of our data is selected. So now we can go ahead and go in and add the trend line to this. So add trend line, which it did. We want a linear trend line for sure. We want to display the equation on the chart. And then going back to our trend line, we also want to display the r squared value to make sure that it fits within the acceptable range specified on your handout. One thing we definitely don't want to do is say set intercept. That sets it to the intercept of 0, which simply isn't true based on the absorbance values when we have 0 protein concentration, because our copper complex does have some absorbance even if it's not forming the 4 different interactions with both the biuret as well as the protein complex. So we do not want to say set intercept there. So this gives us our formula, our y equals mx plus b equation, as well as our r squared value. So if that r squared value is significantly less, that means we have a significant data issue. So let's say we typed in our second absorbance with a concentration of 2 milligrams per milliliter, and we said instead of 0.199, it was 0.999. Our data is substantially off, so our y equals mx plus b equation was adjusted substantially to correct for this number here. Clearly, this is an outlier within our data set, so we'd have a significant issue there. So if there's a typo, go ahead and correct that. If it's something that you saw experimentally, then you'll have to just redo that set. So ideally, in lab, you'd want to graph this before you leave. Fortunately, we have a pretty clean data set here, and we have our curve where we can use our y equals mx plus b equation to now calculate for our unknown concentration values. Okay, looking at our y equals mx plus b equation, we have the y value. So we have the absorbance. I'm actually going to go ahead and just average the two absorbances of these, so we are only plugging in one number. So that is going to be the first absorbance times this, plus the second absorbance, and that is going to be in parentheses. And we are going to then divide that by 2. So that is our average, 0.34. That makes sense. The second one will do the same. We'll go ahead and put the parentheses first so Excel isn't confused by that. So we'll add the two together and then divide by 2 to get our two average values. So then we can use our y equals mx plus b equation. So now we know that, I'll just type it down here. So for our unknown 1, our y value is 0.34. So 0.34 equals 0.0506 times x plus 0.0684. So then all we need to do is solve for x. So solving for x, we're going to take both sides minus our 0.0684, and then once we have that, we'll then divide both sides by 0.0506, and that'll give us our x value, and our x value is the concentration of the unknown. Hopefully, looking at 0.34, so for just above 0.3, so 0.34 is about right there. So hopefully you get a concentration of about 5 milligrams per milliliter for that. But you need to go back and correct because we know we diluted that. Okay, so let's just pick a random number here. Let's say our concentration ends up being 8 milligrams per milliliter. So that's obviously a little bit off. We said it was going to be closer to about 5, but let's just say 8, hypothetically. So if we have that, 8 milligrams per milliliter is not the actual concentration of unknown 1 because we originally diluted unknown 1 before the experiment. So we need to go back and incorporate our C1 V1 equals C2 V2 equation, and for concentration 1 we will say that is 8 milligrams per milliliter, and for the volume was 1 milliliter or 1,000 microliters. For C2, that's in this case what we're solving for, and for V2, we know that the volume of that original solution we used for unknown 1 was 500 microliters. So that's why I've got 500 microliters there. So we want to know what the concentration of our 500 microliter solution is. So solving for this, we have 8,000 on this side. We've got x times 500 on this side, so we'll divide both sides by 500. So 8,000 divided by 500. 8,000 divided by 500 equals 16. So in this case, our concentration 2 would be 16 milligrams per milliliter. So that's essentially the correction, since we know we diluted this by half, which in this case is pretty easy. We know we half diluted it, so you could just essentially double this. That would get us 16. If we've got a little bit more complexity, then it's probably going to be easier to use your C1 V1 equals C2 V2, like when assessing your concentration of unknown 2.